In today's lesson, we are going to be looking at angles in standard position. So this is going to be some new content in terms of trig that you may not have heard or may not have learned before, but really it's just a different way of getting some information for our right angle triangles. So while it might be slightly new, the overall main concepts are things that we've looked at in the past. So a little bit of review. The intersection of the x-axis and the y-axis, again remember vertical and horizontal, those are our two axes. They create four regions that we call quadrants. And they are numbered counterclockwise starting in the upper right. So we start with quadrant 1. This is the main one that we're used to seeing generally, and we go counterclockwise. So quadrant 1, quadrant 2, 3, and 4. So when we're dealing with our right angle trig, we're going to be imagining, or we're going to be looking at points on a grid to come up with our triangles. So you can imagine how this kind of relates to things in the real world, right? If you're plotting coordinates on a grid, or you're mapping things out, or in any software, right? If you're using like a grid system in terms of movement, things like that, this is where this would come into play. So some useful terminology. Standard position, which is what we're dealing with, is an angle measured on the Cartesian plane, so just our x and y grid, measured from the positive x-axis. So the angle is measured from the positive x-axis, which we call the initial arm, to the terminal arm. So imagine, and we can kind of see it here with our kind of key points laid out. Imagine we have our axes, we have a line for part of our angle along the x-axis, along the positive side. We then have our angle that's formed between our positive x-axis and another line, which we call the terminal arm. And generally speaking, this rotates counterclockwise. So it goes from quadrant 1 to 2 to 3 to 4. And then this angle is formed between that initial arm and the terminal arm. And it bends at the origin, or the vertex is at the origin. So that's essentially what we're looking at in terms of our angles. Now you might be thinking, okay, well, how does this apply to trig? It just looks like we're dealing with angles. We'll take a look at that in a second. But again, just the understanding of what the standard position means. Basically, we're looking at an angle that's formed from the positive x-axis to another line rotated counterclockwise. So when dealing with trig ratios, any point on the terminal arm, right, so the terminal arm is the one that's rotated out. It's where the angle's formed to. Any point along that terminal arm, we can draw a vertical line. Let me use better. We can draw, so we have our point here. We can draw a vertical line straight down to our x-axis. And now do we start to see a right angle triangle? We should, because the angle is formed with the x-axis. So if I draw a vertical line straight down from that specific point, hopefully now we can see this triangle being formed. R is what we call the length of the terminal arm, which is the hypotenuse. X, so if I look at x, where would my x value end up being? Well, x represents the horizontal shift, so that's x, that's y. In relation to my angle, which is always going to be in this position when we're dealing with standard position, x is then going to be adjacent to my angle. So x is another word for the adjacent. Y is the opposite. It's across from that angle. And then r we said was the hypotenuse because it's the longest side, and it's also across from the 90-degree angle. So now hopefully you can see how we can kind of come up with trig ratios for standard position. Right, we're basically using a line and a point to create a right angle triangle, and then labeling again our three main sides for right angle trig. So what would my three trig ratios look like? Given that I have a point on a terminal arm, set x and y. So again, if we label it HOA, well, sine, we said, was opposite over hypotenuse, which now we can say is y over r, because y is what we call our opposite in this scenario. Cosine was adjacent over hypotenuse, but now adjacent is x and our hypotenuse is r. And finally tan was opposite over adjacent, so, but now with our standard position, tan is now y over x. It's still the same thing, just now we have specific values because we are using a grid system, not just regular triangles or triangles that we come up with. So we want to determine the trig ratios for the point P, which is 3, 4. So if we imagine that this point here is 3, 4, I'm going to draw my vertical line down. I now should see my right angle triangle. X is the horizontal, or 3 in this case. Y is the vertical, or 4. We don't have R. But how could I find out the length of R, or the length of the terminal arm to that point? How can I find out the hypotenuse of a right angle triangle? Well, we did talk about a specific theorem, or rule, or not rule, but a specific theorem, which was the sum of squares, or previously known as the Pythagorean theorem. So, in this case, the Pythagorean theorem, or the sum of squares, would be x squared plus y squared equals r squared. So this is the sum of squares, or Pythagorean theorem. So I know what my x is. It's 3, so 3 squared plus 4 squared equals r squared. 9 plus 16 equals r squared. 25 equals r squared. Square root that, so 5 equals r. So I know that this is equal to 5. Now I can come up with my trig ratios. Right, sine of theta is opposite over hypotenuse, or in this case, 4 over 5. Actually, let me just write it out, opposite over hypotenuse. I'll just write it out fully just so we can remember or keep on refreshing ourselves. So 4 over 5. Cosine is adjacent over hypotenuse, which is 3 over 5. And then finally tan is opposite over adjacent, which is now 4 over 3. So that's how we would come up with our trig ratios using standard form and being given a point on the terminal arm. So we're just going to go through a couple examples. So given the point P57 that lies on the terminal arm of an angle in standard position, we want to sketch the diagram of the angle. Well, we know that it has to start from this initial arm along the x-axis. We know the terminal arm is going to have a point 5,7 on it, so let's sketch roughly where 5,7 would be. Let's say it's roughly here, 5 is here, say 7 is up here, so we would have a point here on the terminal arm, so I'd draw an arm out, and then my angle would be right there. So that's the 0.57. So that's how we would sketch it. Just roughly draw where that terminal arm would be and where we can see that angle. Given that point, we want to find the distance from the origin to that point. So again, the origin is 0, 0. Right, so imagine it goes out to 0.57. Now again, we talked about how to find the distance or the length of that line. We can form a right angle. 5 is the x, 7 is the y. So if I want to find r, or that distance, r squared equals x squared plus y squared. Just a variation of the sum of squares. R squared equals 5 squared plus 7 squared. R squared equals 25 plus 49. Again, I'm just going through this fully so you can see where all the numbers are coming from. R squared equals 74. I then need to square root both sides to cancel it out. And I'm left with r is equal to 8.6. So the distance from the origin to that point is 8.6. Given that point again, let's come up with the primary trig ratios. So again, I'm going to roughly draw out my terminal arm. It does form a right angle triangle we previously saw. So if this is the 0.57, we said that that was 7, this was 5, and we previously found that this was 8.6. Now I want to come up with my trig ratios. So again, my angle is down here. That's always where our angle is. So sine of theta equals opposite over hypotenuse, or 7 over 8.6. Cosine theta is adjacent over hypotenuse, or 5 over 8.6. And tan theta is equal to opposite over adjacent, which is 7 over 5. So there we have our 3 trig ratios for our angle in standard position given that specific point. Moving on to the next one. Now what we want to do is we want to determine the angle. So what is the angle with this given point lying on the terminal arm? So I'm just going to redraw our triangle. Notice this theta. Notice this was 7. This was 5 because of the 0.57. And then we found that this was, I believe it was 8.6. Yes. 8.6. There we go. So we had 3 different trig ratios to figure out our angle. Right? In this case, it doesn't really matter which one we use. But let's just go through and take a look at all of them. Right? So sine theta equals opposite, so 7 over 8.6. Theta equals sine -1, 7 over 8.6. We get an angle of 54.5. Now if I go through and do the same for all the other ones, cosine theta equals, not 7 because now it's adjacent, so 5 over 8.6. Cosine -1, 5 over 8.6. We end up with 54.5 degrees. And then finally, tan theta, opposite over adjacent, so 7 over 5. So theta is tan -1, 7 over 5. And Again, we should get 54.5, but let's just double check anyways. We do get 54.5. So again, it doesn't really matter in this case which one we choose because we do get the same answer regardless. Let's look at one more example, except now we're going to look at a point in another position. So in a different position. So here we have the point -4, 2 that lies on the terminal arm of an angle in standard position. So if I find -4, 2, -4 on the x, 2 on the y, and then my angle, again, remember the angle comes from the initial arm or the x-axis on the positive side. So that's what it looks like. So a little bit different than the last one. And we're going to go through the same questions. Determine the distance from the origin to the point. Well, if I draw my line out, this is -4, 2. I can still make a right angle triangle to -4 and r and go through the same steps. X squared plus y squared equals r squared. -4 squared plus 2 squared equals r squared. 16 plus 4 equals r squared. 20 equals r squared. So the square root of 20, which is 4.5 equals r. So I know my radius now is 4.5. So again, same steps as before. We do want to make sure that we have brackets when we're dealing with these negative numbers. So you want to include the brackets to make sure that when we square it, we get our positive number. If you don't include the brackets, depending on your calculator, it may not carry that negative through, so you won't get a positive number. Now we want to come up with the primary trig ratios. So again, I'm going to draw out my terminal arm, P -4, 2. We have 4.6, we have 2, and we have -4. So even though this is the theta that we're dealing with, we're going to still be dealing with this angle inside, because then that can help us find the other one if we need to, or which we do, or because that would be the angle of it in standard position. So we can find this angle here in our triangle. So we're still dealing with the angle that's formed off of the x-axis. So that means that this is still the opposite, this is still the adjacent, this is still the hypotenuse. So let's go through and write our trig ratios. So sine theta equals opposite over hypotenuse, or 2 over 4.6. Cosine theta is the adjacent over hypotenuse, so -4 over 4.6. And tan theta is opposite over adjacent, or 2 over -4. So those are our three trig ratios for that angle. Or you might say, well, technically it's 180 minus those because of the supplementary angle rule. So let's determine that angle. So if we want to go through, we know 4.6 to -4 to find our unknown angle x, which we can then use to find theta, which is part of our terminal arm. So I'm going to draw my terminal arm in red here, just so we can, or where the angle that we're trying to find is. So we had our trig ratios from before. Let's go through and solve for all of them just to show that it does work. So sine theta is equal to opposite over hypotenuse, so 2 over 4.6. Theta is equal to sine negative 1, 2 over 4.6. And we end up with 25.8. Cosine theta is equal to adjacent or negative 4 over hypotenuse, 4.6. Theta equals cosine negative 1 of that fraction or ratio. Here we get 150. Something is off. Adjacent over hypotenuse, we got 150. Well, let's go through and check tan. So tan theta is opposite over adjacent, so 2 over negative 4. Inverse of tan, 2 over negative 4. Oops. And I get negative 26.6. So I get 3 different answers. So which one is correct? Which one works? I see tan and sine are relatively close together. But and cosine is completely different. So which one is correct? So the reason we have 3 different answers comes down to the fact that we're dealing with some negative numbers. Now, if we were to take our triangle or our terminal arm, draw it out, we have our axes going down here. Actually, let me keep our axes there. We'll draw our terminal arm here. We have our angle. Now this angle x would technically be the exact same of a mirror image of the terminal arm on the other side of x. And then this unknown value here, y, is actually x, or 180 minus x. So with the way the ratios work, it's actually found us 3 different things. Now, part of it came from the fact that when we square rooted 20, we rounded our answer. So technically, sine theta should equal negative tan theta when the point lies in the opposite side, and sine theta will equal 180 minus, or sorry, cosine theta, we'll put it that way. Cosine theta will equal 180 minus sine theta. And you can say tan theta will equal negative sine theta. So it's just a different relationships. So again, we kind of get similar parts that are kind of related, because it's dealing with negative numbers, or technically because the terminal angle is technically obtuse, it does give us some varying answers. And this is again mostly why when we deal with these trig ratios, we deal with right angles. But again, the main thing is maybe not so much determining the angle, but more so, can you come up with the trig ratios? Can you come up with the length of the terminal arm to a specific point? Can you sketch what the terminal arm and angle looks like? That's the key thing that we're looking for here, because then if you can come up with those trig ratios, you can come up with answers, and then it's just interpreting those answers like we did here. So again, just make sure you understand what or how to deal with angles in standard position.